last class we have seen about inverted indexing. Okay, this is also known as posting file. So let us continue yesterday's class. One second. So we know what is a posting list, what is posting, what is dictionary, and what is inverted file. Okay, inverted file is nothing but your final outcome after you just find out the location and representing it along with the term. Okay, that is your posting list or inverted file. Okay, I just search it. Okay, so we have seen one example yesterday. This one. So this was the example. Chicken address are Jamie. Okay. Okay. Now, let us see the example once again. So we have two documents here. Document 1 consists of some set of information, which is also known as set of terms. And in document 2, we have another set of information. So all together, this document 1, document 2, we call as a collection. Okay, that's a collection. So our collection consists of two documents. Our collection consists of two documents, and each document contains some set of information. These informations are known as terms. So I is the term, dig is the term, make is the term. So initially what you have to do is you have to write all the terms and you have to write the document IDs. So document ID is nothing but to understand, instead of writing doc1, doc1, doc1 or doc2, 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 document 2, we are just giving some ID so that we can write in short. So instead of document 1, we are representing with an ID 1. And for document 2, we are representing with an ID 2. So 1 and 2 represents document 1 and document 2. So document IDs are written down here along with its respective terms. Now, here we are arranging it in alphabetical order. We are arranging it in alphabetical order. So we are starting with ambitious, B, Brutus, capital, and respective document IDs are written down here. So the final outcome it will be, you will be writing your term and you will be writing your document frequency associated with the posting list. Associated with the posting list. Okay, posting list is nothing but your location. So ambitious document frequency is 1 and it is present in document 2. So I'm writing 2 here. Similarly, B, it is present in the document frequency is 1 and it is present in document 2. So we have written down for all the terms. So the left side, this part, the third part, this is known as the inverted file, okay, or inverted indexing. Now, another example is also given here. We have two documents, first come, first serve. last in, first out. So for these two documents, I have constructed the inverted index. So this has also been explained yesterday. Anyway, I'm repeating this once again. So for come, the first one, so in alphabetical order, directly I'm writing the last part, okay. So alphabetical order I have arranged. Then we have here document frequency. So I'm writing down the document frequency. So in how many documents the term belongs. Okay, document frequency is nothing but in how many documents the term belongs. So come is there in D1 only. Okay, it's not there in D2. So it occurs one time in document D1. So 1. So first it's there in D1, but not, it is also there in D2. So in how many documents it is there? In 2 documents. So that document frequency we are counting here, not the term frequency. If I ask you term frequency, then there are 1, 2, 3. So there are 3. Term frequency, if I say for first, you have to say the number 3. But here, document frequency. So in how many documents the term first belongs. So first belongs to document D1, first belongs in document D2. So in 2 documents. That's why we have written down here 2. So this is very important to identify document frequency and term frequency, and it is also it will be also asked in your exam also, to differentiate between document frequency and term frequency, so you don't get confused with these two terms. And there will be lots of calculations in your upcoming chapters. There, if you don't identify properly the document frequency and term frequency, then your answers will be all wrong, because it's full calculations. Okay, so chapter 1 and 2 up to chapter 3 there is not much calculation, uh, but from chapter 4 there will be lots of calculations. Okay, so we find out all the document frequency here. So the document frequency and its respective question list is written down here. So come is there in D1, first is there in D1 and D2, in is there in D2, last is there in D2, out is there in D2, served is there in D1. Now coming to next one. So English tutorial and fast track, learning Latin semantic indexing, book on semantic indexing, advance in structure and semantic indexing, analysis of Latin structures. So these are some examples where you can solve, where you can construct inverted index. So can you construct inverted index for this? Can you construct inverted index for this?
Yes, ma'am.
Okay, so now you construct and tell me the answer. So here I have written an, on, in, and off. It's nothing but this kind of words are called stop words, which we will be discussing in the next chapter. Stop words. Okay, so where sometimes in the question we may get like this, use stop words or ignore stop words, like that. So if it is asked to include stop words, then you have to include all these as an individual terms, and you should consider as an individual term. On you have to consider as an individual term. In also you have to consider. Op also you have to consider as an individual term. But if it is asked that to ignore stop words, then you can directly take off search words and you can use only the other remaining specific words. Because why do we sometimes need to ignore stop words is that when there is large collection. So here we are dealing only with 4 or 5 documents, 6 documents, 8 documents, 10 documents. But if there are 100 documents, for example, there will be lots of and, on, if, to, was, like this. So there will be lots of such kind of words which is not that useful. Okay, because here in this English is an important word, tutorial is a specific word, fast is a specific word, track is a specific word. But when you consider an, of, the, to, these are all words which we use in the document but not that useful. So we can sometimes ignore such words. So these words are known as stop words. So we can directly stop it or we can directly remove it from the collection. And we can use the remaining words to construct your inverted index or to perform your index compression, you perform your index construction. There will be lots of operations where you can perform without using the stop words. Okay, that's why I'm just writing here. These are known as, such kind of words are known as stop words. Okay. So, but for now, you include all because I will be teaching about stop words in our next class. So that in that time, you can ignore the stop words. But for now, you include everything and you construct the inverted index. Okay, inverted index or inverted file or posting file. So all these terms it can be used. So now you construct inverted index and tell me the final posting list of each terms. So all of you must do okay. So let me just move on. I will ask you after this slides. So next one is, so you construct this one, okay? So let me ask you after I complete this one. Processing Boolean queries. So processing Boolean queries is just now what we have done, the logical solving the Boolean expressions which we have done in Boolean retrieval. Okay, so normally here we will be using a function called intersection. So in this we will be using a function called intersection, and intersection we can represent using the AND operator. Intersection means what? It should be there both in the separate events. So if I have two set of events A and B, so A contains some set of elements and B contains some set of elements. So A intersection B represents that the result what we retrieve should be there both in set A and in B also. So set theory, okay, don't you remember the set theory, intersection. So in intersection, in logical operator, we represent it by N. Okay. So intersection operation we are going to perform. So in order to perform the intersection operation, we have 5 steps. 5 steps. First step is locate Brutus in the dictionary. So this is an example. See from your textbook. This what I have written here: Brutus, Calpurnia, intersection. Sorry, Brutus, Calpurnia. All these examples what I have done here. This is the example from your textbook. You can also refer your textbook. Your textbook name is, one second, uh, Introduction to Information Retrieval. Okay, your textbook name is Introduction to Information Retrieval by Christopher D. Manning. Christopher D. Manning, Manning. Okay, Christopher D. Manning. So I think I also have a ebook for this. I will share you the ebook today so that you can refer your textbook. So Brutus, Calpurnia, Caesar, Julius, these are some documents, some information we take out from your this Shakespeare, some novel or some book. Okay, from that we have taken out this one. Okay, so using these examples, most of the examples are solved in your textbook using this Julius Caesar example. Okay, it's a book called Antony and Cleopatra Act 3, some scene, some drama, some book written by Shakespeare. Okay, from that we have taken out some set up information, and from using the information we are solving the examples or solving the problems. Okay, so now, okay, the question here is, uh, the first step here is locate Brutus in the dictionary. So in the dictionary means from your collection, from your information, you have to locate Brutus. And second one is retrieve each postings. Retrieve is each postings. Then locate, one second. Just give me 1 second. Just 1 minute, okay? Okay. So initially what we have to do is we have to locate Brutus in the dictionary and we have to retrieve its posting. Okay. So you can see down there Brutus. Then this is the posting we have retrieved. That means Brutus is there in document 1, Brutus is there in 2, 4, 11, 31, 45, 173 and 174. Similarly, you have to locate Calpurnia in the dictionary, retrieve its posting, and finally you have to intersect the two posting list. Okay, this example is for this intersection operation, Brutus and Calpurnia. Okay, now we are locating Brutus. We are finding Brutus where the Brutus term is. Then we are retrieving its postings. So we are finding Calpurnia and we are retrieving its postings. And finally we intersect this. So how do we intersect? We are just taking out the common uh, postings from the two retrieved postings. So 2 is common here and 31 is common here. So this is intersection. Okay. Now algorithm for intersection. Algorithm for intersection. So you can see here intersect posting 1 and posting 2, P1 and P2. It is represented by P1 and P2. We are going to intersect two postings. Then while P1 is not equal to nil and P2 not equal to nil, that means when both the postings are not empty, when both the postings, if it is empty, we cannot perform any intersection operation. So when it is not empty, we are going to perform the intersection operation. So when P1, posting 1 and posting 2 are not empty, only then we can proceed with the posting with the intersection operation. So if document ID of posting 1 is equal to document ID of posting 2, that means if the two IDs in the two postings are equal, only then that will return your result. That means we are going to add this document ID in the answer. Initially answer is empty here. So 1 shows an empty answer. So if answer contains no element. Okay. Now if document ID of posting 1 and document ID of posting 2 are equal, if these two IDs are equal, then we are going to add that document ID in the answer. We are going to add document ID in the answer. So we are checking is P1 posting 1's document ID is equal to posting 2's document ID. If it is equal, then we are adding posting 1's document ID to the answer. Now P1 next of P1. Then in P1, see here in this example, suppose this is the posting 1, this is the posting 2. So P1 is nothing but the first location. First location we are going to check with this one. Okay. Calpurnia Brutus 1, we are going to check with the Calpurnia 2. So if these two IDs are equal, we will return 1 to the answer. And if it is not equal, then we will increment one location and we will move on and we will check with the next ID. Okay. But if it is equal also, we will return the result and we will move on to the next posting list. That is what it is said here. So you can check here P1 next, P2 next. This condition is for when the two document IDs are equal. For posting 1, the first position, posting 2, the first position. If the two locations are equal, then we will return the result. It will return the result and it will move on to the next location. Okay. So after moving on to the next location, again this will be repeated. We will check the IDs and if it is same, then we will move on to the next location. Again, so this loop will continue. It will be repeated until you finish all the posting lists. But when if the two document IDs are not equal, so we have a condition here. Since document ID of posting list 1 is less than document ID of posting 2. So if it is less than posting 2, then we will increment the posting list 1. Okay, we will increment the posting list 1 and that means we will move on to the next position. Otherwise, we will move on for the next position of posting list 2 and we will return the result. So here you don't get confused with the algorithm. The algorithm is very easy. What it says is initially first position. Normally when you write the posting list, it will be sorted. That means it will start from 1, 2, 3, goes on like this. Okay, so the first position is 1, the first position of the second term is 2. For Brutus is 1, for Calpurnia is 2. Suppose for Calpurnia it is also 1. Instead of 2 it is 1. So 1 and 1 is equal. The document IDs are equal. So 1 we will return to the answer. So in your answer 1 is there. Okay. Then we will move on to the next position 2 and this 31. So we are considering the first value as 1. Okay. So now this is 2. If this is also 2, then these 2 are equal. So since it is equal, we will return 2 and we will add answer 2. So in answer already 1 is there. We are adding 2. Okay. So let me just write here. Suppose, so in your answer, already 1 we have written considering when the first position of Calpurnia is 1. And for Brutus, the second position is 2. For Calpurnia, let us consider the second position also 2. So 2, 2, these are equal. So we will return 2 in the answer. Like this it will go on. Okay. For the similar, when the two document IDs are equal. But when, if the document IDs are not equal, if the document IDs are not equal, we will check the posting list of 1 document ID of P1 less than document ID of P2. Document ID of 1 less than document ID of P2. So that means 1 less than 2. Okay, 1 is less than 2. This is document ID of P1. This is document ID of P2. For Calpurnia, this is document ID of P2, document ID of P1. So 1 less than 2. So 1 less than 2 is correct. So if it is correct, what you have to do? You have to move on next position. That means if the condition is correct, the document IDs are not equal, right? So we have to move on the next position 2. So this remains the same position. Okay, we are moving only the first one, posting list 1 position. Since the condition here, the condition 1 less than 2 is correct, since it is correct, what we have to do? We will move on 1 position next to Brutus. Okay, for this Brutus, this posting, next position we are moving. Now we are in 2. So next time what you have to do is, secondly you have to check 2 less than 2. So this is wrong. Since this is wrong, 2 less than 2 is wrong. What does your condition says here? Your condition says you have to move the position of this one, next position of P2. So you have to move next position of P2. So this will be 31. Okay. For equal condition, I already told you the equal condition, if both are equal, we are going to return, and if it is not equal only, we will go through. So since let us consider if it is not equal, then we will move on to the next position. Okay. So this process follows until all the posting lists are checked, and only the equal document IDs we are going to return. Okay, that will be our result for intersection operation. So this example, truly you can easily understand by seeing this example. So 1 and 2 it's not equal, so we will move on to 2 and 2 it is equal. For equal condition we will retrieve 2 in the answer, so 2 will be there. Okay, now 4, and now 4 and 2, now 4 and 31, like this it will move on. Okay, so now 4 and 54 not equal, 4 and 101 not equal. Then with 11, you have to check with this. With 11, you have to check with this. Similarly, for 31, you have to check with this. You have to check with this. 31 and 31, it is same. You are going to add 31 in the answer. And it goes on until you complete all the postings. So now we have two similar things here, 2 and 31. So our intersection result will be 2 and 31. And this is also same thing, but for n terms. Here we are considering only posting 1 and posting 2. That means we have considered only for 2 terms. But when there are more than 2 terms, we are using n here. Instead of P1 and P2, there will be Pn or Tn. Okay, this is nothing but the term. Term 1, term 2, term 3, term 4, up to Tn. Term n terms are there. Okay. So initially, the same operation we are going to perform for n terms also. So sort by increased frequency, that means you have to sort the terms here. What we have written down here, for terms also you have to sort, and this postings it is already sorted one. For terms also you have to sort, that means you have to write in alphabetical order. Okay. Other things, operations are same. So you are going to check for the first term, you are going to check for the second term, third term, and the rest of the terms you have to check. And when you check it, you have to check if both the terms are, both the posting, all the postings are not empty. You have to check all the term, all the postings are not empty. If it is empty, it will return no result. So it will return a zero value. So in order to return a non-zero, you have to check if the postings are not empty. Now we will see an example so that you can understand it more. So recommend a query processing order for the following query: tangerine or trees, and marmalade or skis, and kaleidoscope or eyes, given the following posting list size. So you have to consider 2 as one posting. These are not sorted. Okay, these are not sorted. You can sort it and you can solve it. Okay, operations we have already done, right? Or operation we have done, and operation we have done. So perform tangerine or trees. First one, you perform tangerine or trees. So there are 2 document 6. So you can write only one ID. So that if it is sorted for tangerine, it will be 3, 4, 5, and 6. Okay. So for example, for tangerine, the posting list will be, sorted posting list will be 3, 4, 5, and 6. Okay. So you can write in a box. You can write in a box. Similarly, you have to sort all the postings and you solve. Tell me the answer. Tangerine or trees, marmalade or skis, kaleidoscope or eyes, and finally you have to perform intersection operation. Okay, first we can perform this 2 and operation. The result we can perform an operation with this one. Okay, so now tell me what tangerine or trees. What is the result?
Ma'am, will it be 1, 2, 3, 4, 5, 6, 8?
Okay. Marmalade or skis? For marmalade or skis, what is the result?
Ma'am, 0, 1, 2, 3, 5, 6, 7, 8, 9.
Okay, kaleidoscope or ice?
Ma'am, 0, 1, 2, 3, 7, 8, 9.
Okay. So here one more point you need to know. Zero I'm using here as a document ID. So when you solve it, you can just include zero. Okay. Or else sometimes if it is an empty document, you can just ignore it. But for this particular condition, I'm using zero as a document ID. So D0 can be one document ID. So you can use 0 while solving the answer. So now let us see here. For tangerine, 3, 4, 5 and 6. For trees, 1, 2, 3, 6 and 8. So or means everything will be there. So 1, 2, 3, 4, 5, 6 and 8. So other remaining you solve and final result it will be 1, 2, 3 and 8. So check whether you get 1, 2, 3 and 8, the final result.
Yes, ma'am. That's
Okay, that means you have calculated correctly. So this is how we perform intersection operation using the inverted index. Now coming to next one, tokenization already we have done when we first here the same thing. Tokenization we have done. Tokenization just converting into individual terms. So here also we are explaining it once again. That means we given a character sequence and a defined document unit. Tokenization is the task of chopping it up into pieces. That means we are separating into individual terms. Okay. And we will be taking off the punctuations, commas, apostrophe commas, and all columns and all we will be taking out when we perform tokenization. Okay. So friends, romance, and countrymen. Here, when we perform tokenization, we will remove this comma, we will remove this one, and we will just write friends, romance, and countrymen. Okay. Now, this is after performing this, we will be having the linguistic preprocessing. Linguistic preprocessing also I have explained. So linguistic preprocessing there, we will take out all this plural form as and countrymen, it will be instead of e, it will be a. We are all trying to put into singular form so that it will be the base form. Base form, why do we put base form? Because for a particular term, you may have certain this one. For example, say we get. Suppose get is the GET get. If it is the term, we can have got also. So GOT got. So the past form, the present form. So all these will come into a single form, that is the base form. So we are just putting it into base form. So that comes under linguistic preprocessing. And also we will be taking out all the plural forms. Now here some other examples. Suppose when there is a name Mr. O'Neill, then O'Neill, how there are some issues when we perform tokenization. So that issues we are discussing now. Okay. So Mr. O'Neill. After O there is an apostrophe comma, then nil. So how will we tokenize this one? Whether we are going to write O alone, we are going to write nil alone, or we are going to write O dash nil all together, O apostrophe nil. So there are certain forms here you can see here. There are certain forms. Nil, O apostrophe nil, O separately, nil separately with an apostrophe, and this without apostrophe. So all these are possible. All these are possible. Now, other terms aren't, are not, actually are not. So aren't, for this also you can consider as a single term, single token, or without an apostrophe aren't, or are not, or are if you take out the apostrophe T as a separate term. So these are all possible tokenization tokens which we can derive from this particular ONIL and for this aren't. So these are some issues we faced when we used apostrophe. Okay. Then another issue we will discuss. Examples you can see here. Finland's capital. So whether it will be Finland and S separate tokens, Finland one token, S one token, or we will write Finland's, or we will write all together along with the apostrophe, Finland's. So these are the issue we face using apostrophe in tokenization. And one is hyphenated words. Hyphenated words also, Hewlett-Packard. So for this also Hewlett hyphenated, there is one hyphenated hyphen here. So this hyphen we are going to ignore the hyphen, or we will write Hewlett as a one token, or we will write Packard as one token. These two, whether we have to, this is the two tokens or one token. So again, one second. Okay, so this is also another issue, and San Francisco is the name of the place, but whether it will be one token or whether this will be two tokens. So certain, there are lower cases problem. See, for this co-education hyphenated word, you can say co is one word, education is one word, or co-education we will consider as one token. So like this, for lower case also, hyphenated word. So for hyphenated word, it will be effective when we put all together as single token. Otherwise, it will give you different meaning. Okay, that's why we will perform linguistic preprocessing. Now, so explanation you can just go through, because here I have explained for hyphenated whether it will be two words or whether it will be one token or two tokens, and for Finland's apostrophe also whether it will be two tokens or separate tokens. All this issue they are explaining here. Okay, for co-education and for Hewlett-Packard and San Francisco, name of the places, Los Angeles. So all this, there is the blank space is known as a white space. Okay, so this one, what this is also an issue, and for this purpose we are introducing language identification. Okay, based on the classifier that can sort out this problem. So for hyphenated also, for name of the places which has white space, and also apostrophe, that problem In order to sort out these issues, we have introduced language identification. Okay, so this will use some short character subsequence, and this method will be effective in solving this problem. Sometimes this language identification also, it cannot solve 100%, but it can be effectively used. Okay, now stop words. This is what I told you, stop words. So stop words. These are very common words which appear in the document, but this is of uh, less useful. Okay, so these words are called as stop words. You can see here a, and, are, as, at, be, by, all this. Okay, all these prepositions, all these be form of the verbs, was, where, here, there, this, that. All this comes under stop words. Okay. Now, in order to determine a stop list, we are going to sort the collection frequency. So here again, one more term, there is collection frequency. Collection frequency is the number of times each term appears in the document collection. So in the whole document collection, the number of times. Okay, so if I have 5 documents, in that 5 documents, if I want to search a word called come, so that come you have to search in all the documents, and in a document it occurs how many times also that you have to count. Okay, so this is related with the term frequency. Now, token normalization. So token normalization here is one method to solve the issues we have in the previous one, the string length and hyphenated words. So token normalization here, it is the process of canonicalizing tokens so that matches occur despite superficial differences in the character sequence of the tokens. So here it means nothing but, so if you write anti-discriminatory, then these two will be mapped. So our language identification problem, our language identification process, it's going to return that these two words, these two terms, these two tokens are being normalized into anti-discriminatory, like this. So we can write like this instead of hyphenated word. So because anti-discriminatory, this one, and the hyphenated word, this one, these are normalized using language identification technique, and it will return to you anti-discriminatory. Okay, so this, you can use this as the this as a token for this hyphenated word. Here also some example windows. So this query term windows, it will make windows in the document. So you can write this window with the case sensitive one, WINDOW. This third one you can write. So this will match or map with window document, with this window also, with this window also. So it will map with all these forms in your document with this particular term window, because with language identification all this will be mapped and it will be normalized. Okay, so when I write window, it can return windows also, it can return window also. Now another technique for solving those issues, we have stemming and lemmatization. So stemming and lemmatization we will do tomorrow, because this will take, I cannot complete today, so it will take some time. Not very long, but I cannot complete by today, stemming and lemmatization. So we will do tomorrow. So before that, I'll take a quick roll call. You answer to your response to your roll call. So only few slides are there, but anyway.